Hello,
Yes, good morning.
morning. Oh, Abdullah is missing. So you are taking both places. But I assume everyone is here. Homework 7. You are homework 16. Readable? Niranjan, is it readable?
Yeah, I can read.
So we introduced the idea of analytic function on a complex plane. Analytic function is often, I have noticed, used in the context of real variables also, but here we are meaning complex variables. It's different. Both of them mean derivative, but analytic function on a complex plane is significantly more richer and much more constrained and has more features in it. So we have analytic and so on a complex plane. And we said what are the requirements for an analytic condition? At least that is a necessary condition, not sufficient. And let's begin by, let's say that it's Z, which is x plus I y. It's basically for various purposes two-dimensional plane, but that doesn't mean that the vector space is the same. Like vector space is also a two-dimensional plane, but here we can divide. That's the basic difference. You call it the complex multiplication is the division algebra. This is the real part of the complex number. That's the imaginary part. Say there is Z in here, and you take any point. Say there is a domain which is the whole of your xy plane, and you can take it to another plane. So this is f of Z now, and this can be written as u of xy plus I times v xy. And again, since this has two variables in it, you can think of for every point, there is a point in here. It's a one-to-one mapping. There is a u and a v, and this is the complex plane associated with the function f. Okay, so Z corresponds to F here. It doesn't have to be necessarily going into this plane. It could be anywhere here. So that's the F. You will notice that here there are two variables, X and Y. But even though Z is X plus IY, there is a single variable Z there, and we will address that in a few minutes. An analytic function has this necessary condition, which is called the Cauchy Riemann conditions. And that is that the partial derivative of u with respect to x has to be equal to the partial derivative of v with respect to y, and also partial derivative of u with respect to y is equal to negative of partial derivative of v with respect to x. So that's at least one condition necessarily it has to satisfy. Even if it satisfies, that doesn't mean that it is necessarily analytic, especially at a certain point, it might be infinite there and still have these features available. So there are some examples I've given in the homework that you should look for, that even though this is satisfied, you may not have an analytic function. So that's one thing you want to look for. If this is the case, we should also, I also want to emphasize, or I think if you have z is equal to x plus iy, as I said, there is only one variable, but the second variable you can think of is z star. And immediately you can invert this. So x can be equal to z plus z star over 2, and y can be z minus z star complex conjugate over 2 times I. And then you would say that, okay, what about derivatives? If I have a derivative with respect to z, now I should think of it as x and y, it's a partial derivative. So this can be d by dx, z times d by dx, so chain rule. And x with respect to z is 1 by 2, so it's 1 by 2 by dx. And when it comes to d by dy by dz is 1 over 2i. So that's minus I over 2 by 1. That's one derivative. And the second is d by dz star, do the same thing. Right. And this comes out to be, again, x with respect to z star is again 1 by 2. But now y with respect to z star is minus 1 over 2i, multiply the I on both sides, so it is plus I by 2. Using this, now again you look for what does this Cauchy-Riemann conditions look like. So Cauchy-Riemann conditions look very simple now in terms of z and z. Riemann condition again is basically derivative, partial derivative of the complex function with respect to z star is equal to 0. So analytic function means that in general, this could have been a function of z and z star. If there is no z star, that means the Cauchy-Riemann conditions are satisfied. So when you think of it in terms of z star, it's very easy to at least algebraically see that. Geometrically, not necessarily a very useful, insightful relation. It is as obtuse as the partial derivatives in u and v, but at least algebraically you know that there could be no z star in the expression for the function. So that's your derivative. So if you have such a feature, then you can have a derivative. There's also one nice, very nice relation you can prove. I think there is something related to this in your homework also, even though I don't ask you to do this for all orders. And the homework is that if there is an analytic function, the first derivative of an analytic function is also an analytic function. And then you can do this in a chain. Second derivative is also analytic, third derivative is also analytic. So if the first derivative exists, you have all the derivatives that exist, and it will be analytic at a given point. If we have an analytic function, now we have a derivative, so we should be able to go and define integration also. So this is complex integration. Integration on a complex plane, maybe that's it. So what we would like to do is, if you have a complex plane, so again x and y, and if we are doing one-dimensional integration with respect to a one variable, the limits are very easy to put in, right? So if, for example, if I'm doing real integration, so this is x, and then it's convenient to put f of x there. F of x and f of z should not be confused. I'm using the same variable f, but this is a one-dimensional function. And if you're doing the integral, you will say this is a, that's your b, that's the area underneath that. So you have an integral of f of x, and if you're doing a definite integral, you would say a to b. Same thing if you're doing on a plane, you would say, now I have to go from point, let's say z1 to point z2. Correct. So I go from point z1 to z2, and I'm on a complex plane now, so it is bz instead of x. This is bz, and that's f of z now. Remember, f here are two different entities. That's a complex integration on a complex plane. Is that sufficient information? Is there anything missing in this? If I were to tell you, think of vector space. If I have to do a line integral on a plane, is that sufficient information? I start from one point, I go to the other point along a line, and that's line integral. I say that's not sufficient information. Is that? Think of a line integral that you're doing in electrodynamics, let's say, on a plane. Or the work done by a force, right? You say along, so work done by a force will be this, right? You do L dotted with force F, and this is our initial to our final, right? So this is a three-dimensional space, so that's your initial to our final. That's the work done by a particle by a force. I say that's not well-defined integral. Why not? Which depends on which path. I have specified only the initial and final points. I have to tell you the path. That's important that I tell you the path, unless it's a conservative force. If it's a conservative force, then it's independent of the path. Then you don't care which path it is. And often we work most of the time with only conservative forces. And in that case, you don't have to specify the path. But in general, this is a path-dependent quantity. In fact, there are very few forces that are conservative. So we need to have a path here. So this path will be when we were doing forces, and in electrodynamics, you really say it is a path here. You will call it the contour. So when I'm going from Z1 to Z2, I want to go along a contour C. That's contour C. Often you won't write the word contour, you will just write the letter C. And somewhere you have to, in words or in a diagram, specify what my contour is. So our complex integration requires a specification of Z also. We would here like to talk about how does integration of an analytic function work like. So let's work on that. So let's assume that let f be analytic. Let f of z be analytic. And whenever we say analytic, it is analytic in a region. It might be analytic on the half side of the plane, but it may not be analytic on the other side of the plane, or it may not be analytic at a point. So let f of z be analytic in a domain, let's say, in a region or a domain, right? In a region of your xy plane, it is analytic. And if that is true, then I can pick an area. So let's say, again, draw xy point, and I pick an area. So that's my surface at area. Then what I have is that partial derivative of z star with respect to f is equal to 0. If my function, the complex function, is analytic, immediately I say this is true. If something is 0 at a certain point or at various points on an area, I can add up all those zeros and it should still be 0 unless I don't multiply it with an infinite. So if it is 0, they will all add up to 0 again. So I do an integration. So integration over this area S. So on area S, and partial derivative of f with respect to z star is equal to 0. Again, notice we have a very similar thing that happens in electrostatics. We have something 0, but when we integrate, we won't get it to be 0. If that is the case, then you say that there is an infinity somewhere there. But here we are doing analytic function, so everything is 0. If there's nothing you're multiplying with it, so it will stay 0. You got to make sure that it stays 0. With that caveat, we are working, so there should be no infinities in there, because infinity multiplied by 0 can't spoil the whole argument. Okay, if that's the case, again we go back to f. The derivative with respect to z star is nothing but this 1 by q. So let's plug that in. So you have dx y, and I have a 1 by q in there. So this is 1 by q d by dx. I won't work in the rectangular coordinates. I'm just deriving a relation, but once I derive it, I won't stay in rectangular coordinates anymore. We will go back to the standard. And f is u plus I e, right? U plus I times e. And the idea is that we should be able to use Riemann conditions, or Cauchy-Riemann conditions, which is basically this. If this is 0, then we are adding up to be 0. But can we say something more than this? And that will be a very nice relation, exactly like electrostatics, where divergence of electric field is equal to a constant, means that there is a delta function there. Similarly, here we will have a pole. We will call that delta function a pole in this. 1 by 2 can go away, and let me do this integration dx dy. And let me now specify this better. So I'm doing an integration on a region, but let me make this a square. And so this area now is f, and it is an infinitely tiny area. So it is at one corner you have x, y. Other corner it is x plus, you go at infinitely tiny distance dx on the x direction, and then this will be x plus dx, go y plus dy, and here it is just x remains the same, y plus dy. So that's on a complex plane, and the same idea is happening here. So you're integrating from x, and let me also call this x1, y1, and this could be x2, y2. So that's just so that I can write since I'm integrating over x, otherwise I'll have to change the variable, dummy variable. So this is x1 to x2, y1, y2. But that's the same idea in there. And 2 can cancel out, a half can cancel out, and what I have is derivative of u with respect to x. And that is a minus derivative of v with respect to y. And plus I times derivative of u with respect to y plus derivative of v with respect to x. And if you notice, this is nothing but your Cauchy Riemann conditions in the in the rectangular coordinates. If this is true, each of this parenthesis is 0. If the square bracket term is 0, integration of that zeros over a small region will be equal to 0. So that's the same statement as here, but now in rectangular coordinates. But now, since it is rectangular coordinates, we can really piece by piece take it apart, and that's what we will do. Let me go here to the next board, and these are partial derivatives, or when I'm doing an integral, it is a total derivative. So let me do that. The first one is x. So I can do this x integral now. So once I have finished that, this is y1 to y2 dy, and the u integral goes from x2 to x1. So it is u of x2 comma y minus of u of x1 comma y. That's it. And x2, remember, is x plus dx, x plus dx, and this is simply x. Right, that's just a short form for that. Second one is v, so that is minus of integral with respect to y can be completed. So what is remaining is an integration with respect to x. That's x1 to x2, and I have v this time. So it is v of x and y2 minus v of x comma y. So I'm completing the integral, one of the integral in each one of the terms. There are 4 terms in there. So plus I, this is y, so y gets completed, what is remaining is x, and this is u of x has to be going on, so it is hold on. Now y, yeah, x keeps going, so it is y2 minus of u of x and y. But yeah, y integral is finished, so I have y1. Same thing, plus I. And now x is completed, so it is y1 to y2 dy, and v of x2 comma y minus the x1. Just basically mechanically, manually doing each of the chunks. This proof is analogous to how you would have proved if you have ever done divergence theorem, if you have proved divergence theorem or curl theorem, Stokes theorem, any of those proofs, you usually take a small piece box and then you verify that. But once you make the conclusion, it is true for any region, any point. So let's collect this now. So let's see, how can I do this? So let me start with here. So there is a u, and we connect these two. So these two are the same. U and a v. So let me plot these terms. So that's an I integral dx going from x1 to x2, and just basically rearranging it. So u of x comma y2, and this is plus iv, I suppose, plus iv x comma y2. So I started from here and I added to this. I'm basically mixing things. And the main idea is that this is nothing but the analytic function itself. This whole piece here is f of x comma y cubed. Right? I can start collecting f there. So that's the main idea. And the same thing goes in with here also, right? X and y1. So it is minus of I times x1 to x2 x, and yeah, I don't need the square bracket this course. So this is minus has been taken care of, I has been taken care of, so it is u of x comma y1 plus, so minus I z, so it is plus I v of x comma y. Hopefully it's clear what I'm trying to do in the next step. This should be very clear, because this will be like I'm putting it back once I've done the integral. I'm putting it back in terms of the analytic function. Do the same thing here. This time it is y, so it is u and a y, so it is plus y1 to y2 dy, and u of x2 comma y, and this one is plus I times v of x2 comma y, and this is in there now minus of both side here. Whole thing is 0. That has this nice feature, and that is that you have plus I. Let me multiply that I all over, so I think I don't need that. And here it is plus, so this is I will do an I square, right? So it is minus I squared put in here, and minus I squared. I introduce that and then cancel out one of the i's. So what I have remaining is x1 to x2, right? x1 to x2, keeping y fixed, so that's along the horizontal line. We'll come to that, and that's your f of I mixed up, right? So this is x1 to x2 dx, and then f of x comma y2, and this is the same thing, f of x comma y1. What did you have to? Just so that I can get rid of the I. Nothing specific. It will later on there will be an I floating around, but I'm just filling it. If that is any confusing, let's see. Doesn't it change the sign? No, I'm removing the I. Let's not confuse. Okay, how about that? So let me not include. If that is any, it will come in the next step. It's just this is the next one I, that's all. So I kind of choose the pattern. So as an I in both, I keep it now. I don't remove it. So and that is other term now. Oh, there was an I. Yeah, there is an I in this, and the other next one doesn't have an I. Right? So this is y1 to y2 dy, and here it is f of x cubed comma y minus presumably minus f of x cubed this was x1, right? No, front to that. When I collected the last ones here, this should have been an x1. Check this. I changed these two, those are taking notes. I changed this x2 to x1 and x2 to x1. And that's equal to good. So now basically what has happened is that I'm back to now the analytic function itself, x, except that it is at different places in the integral, and I have to on the plane, and I have to now do this identify where is this path. So I'm going from x1 to x2, keeping y fixed. x1 to x2, keeping y fixed. x1 to x2. So remember, this is x1, that's x2, keeping y fixed, which is no, that one. I'm going from x1 to x2, keeping y2 fixed. So y2 is here. So that's this plane. That's here. So let me call this 1, 2, 3, 4. Let me also have the clockwise as negative so that counterclockwise is positive. So this is what I would like to identify. So if I go from x2 to x1 along y2 being fixed, that is my path C3. But here I'm going from x1 to x2, keeping y fixed to y2. So this is minus C3. So I'm going to notice what I'm doing. Minus I, this time I do C3. I just say it is C3, and this time I don't have to say dx, I can say this is dz. That dx is a variable along that, so now I can put it back to dz. So on C3, notice, on C3, dz is equal to dx plus I times dy, where dy is 0. Right? You're going along this path. So that's dz, and this one is f of x y now, right? I don't have to really say y2 because y2 is the contour tells me, this path tells me that on this contour y is fixed at y2. So this language now changes to a more generic language. I'm talking in terms of contour. Next one, I'm going from x1 to x2, x1 to x2, keeping y1 fixed. That is in the right direction that I want to. So I say this is minus I of C1 of dz and f of x comma y. Next one. Next one, it is plus. I should be careful. So this is dy now. So this is dy. I'm going from y1 to y2. So y1 to y2, keeping x2 fixed. So I'm on C2. Right. This is C2. But notice on C2, my dz is dx plus I dy. Correct. So this is not really the y. I'm missing an I, and this is the I was trying to put in earlier, so that since it is 0, I don't have to emphasize it so much. So it is I times dy, that is dz. So I put in an I here, and then I will have to put in a minus I. So that's minus I times dz and f of x comma y again. And same thing, you do it for here. So this is equal to minus I. So you're going from y1 to y2, x1 fixed, y1 to y2, x1 fixed, and there is y1 to y2, x1. Oh, again, there is an I that you will introduce, and there is a minus I, but there is already a minus sign in there, so that will be used to change the contour. So that's C4, and that's dz f of x1. That's equal to 0. Minus I is common in the whole thing. I drop that out, and this is nothing but C1 plus C2 plus C3 plus C4 dz f of xy is nothing but f of z. That's equal to 0. C1 plus C2, what I meant here was C1 plus C2 plus C3 plus C4. That's a closed contour, that's a loop, right? That's a special case. So what we're saying is that a closed loop, so often you say closed contour is with an integral with a circle, and we say this is C dz of f of z is equal to 0. Even though I have done this for a square, any curve, any random curve can be broken into squares, right? You can always break this into tiny, tiny curves, and this is true for any contour, and this is called Cauchy here. So, few things we have at this point. Derivative means that it has to satisfy Cauchy-Riemann condition. That's a very restrictive condition on that function. And those functions that satisfy the Cauchy-Riemann condition, you pick any region. So as far as this whole region has no point where it is not analytic, that means at every point the derivative is well defined here, then you do the integral there, it is 0. A very strong statement. This, you see this, where else do you say this? This is in conservative forces, right? Whenever you have a conservative force, if you go along a circle, it will do 0 work. Like gravitational potential energy, if I were to lift this power cord, lift it up, in fact, I can go all the way to moon and then bring it back here and keep it here. And then I ask, what is the work done by the gravitational force? Notice the language. I'm saying, what is the work done by the gravitational force? Not the work done by me, not the work done by my muscle, but the work done by the gravitational force will be exactly 0, because it's a conservative force. Whatever plus energy you put in at anywhere along the path, you will have to do the negative when you come back along. Not necessarily on the same path. You can come along different path. You can go on the left side of the moon and come back to the right side of the moon. As far as you come back home, you do 0 work. That is because the dl dot f that I wrote earlier, the 3-dimensional integral, this is 0 for a conservative force. And a conservative force has this feature that force can be the curl of the force is equal to 0. Like it's like the electric field, right? Curl of the electric field is 0. That means if you go around, so electrostatic energy is also conservative. So you have a potential energy associated with it. Whenever this is possible, it is possible to write a potential energy associated with that force. You have a gravitational potential energy, electrostatic potential energy, and that's all. Not many other potential energies you see, because conservative forces are very rare. We are not doing forces, we are doing a complex function, but there is a very similar, at least features that we are seeing. is that if the function, like there we talk about curl and divergences, if you have a function or an electric field which has zero curl and it has a divergence available, then you say that it has it is conservative. But here what we are saying is that if it is an analytic function, then the path integral along any contour is equal to 0. And we are going to exploit this a lot. In fact, this is one statement using which a lot of things in complex analysis can be achieved. So try to understand the geometry behind this. And now let's use this, at least get one step ahead and say that what about or modify this a little bit statement, which makes it more useful. Okay, so a consequence of that, if you want. So let's call it an example. This is an example, but almost a very useful extension of this theorem, or often you say the consequence of this theorem. Not focused. Oh, yeah, here on this screen. Okay, yeah, you like to see that they're there sometimes. Okay, so let's try to evaluate. So there is an integral I of a, and that's equal to, there is a closed contour C, Z, and F is analytic, and now you divide it by B and Z. So let's see what all this means. We are assuming that F of Z is analytic. Analytic, I don't have to say it is analytic everywhere. It is analytic inside C, let's say. There was a quiz problem last time that find a analytic function that is analytic everywhere. And did you guys attempt on that? Yes, exponential. Yes, easy. Easy is analytic everywhere. Yeah, that's except. What about infinity, or as you get very far away? Right? Yeah, exponential is. Is that what is there in the literature? Where did you guys find this? You guys just figured it out, or? On the internet. On the internet? I think the point is, it is like in complex plane, there is this feature that infinity becomes a little useful. It's not like the usual number line where infinity really doesn't care. We don't care for infinity. Exponential, you would say that has a pole. Yeah, x and y, I mean. Yeah. On the complex plane, it is analytic almost everywhere except at infinity. And maybe I didn't emphasize that so much. I want it to be well defined at infinity also. You can say that it blows up at infinity, right? That's one thing you can say, that it is not well defined at infinity. It is infinity at infinity. Or maybe that's the way I can argue. So maybe if I change my question a little bit, so I was not precise enough. So if I say that I want it to be finite at infinity also, okay, so then can you think of a function? So I give it to you. Yeah, you guys came up with the correct answer, that exponential is analytic everywhere, but then I say, oh, at infinity, it is not well defined. So can you think of a function which is well defined at infinity? That means it goes to 0, or at least doesn't blow up at infinity, and it is analytic everywhere on the complex plane. It turns out sine and cosines are exponentials. So if exponential is not well defined, sine and cosine also will not.
They don't go to infinity.
They do. Now you're on a complex plane.
Maybe a polynomial.
A polynomial will also grow, right? So that's a good point. Like sine and cosine, we always think of it as oscillatory. In a complex plane, it is not oscillatory. Right? So exponential of iz is exponential of ix plus iy. So this is ix and exponential of minus y. This is oscillatory. This is growing, like growing or decaying either way. On one side, it will grow. So once you're on a complex plane, oscillatory functions are or oscillatory everywhere is hard in a sense. So the statement is, this is probably not easy to prove here, is that
Function.
there is no analytic function which is analytic everywhere on the complex plane except a constant function, which is trivial. A constant means just constant everywhere. That's trivial, right? If you take away that, then there is no analytic function, okay, which is analytic everywhere. So that's why when I was writing, if I say f of z is analytic everywhere, then that's too trivial a statement. I would say inside the C. So it could be non-analytic somewhere else in the complex plane. So there is a function which is analytic inside the C. And what is my contour? So let me say that, so this is my complex plane. And somewhere there is a point A. So A is a complex number. So it is somewhere on that complex plane, there is an A. And around that is my contour C. So it goes, and this, and usually in this case it doesn't matter, but most of the time the contour will have a direction associated with it. Use the contour to, or try to make it counterclockwise. It works. Like it is like the right hand rule. If you have done cross product, if you have used Stokes' theorem, you will realize that always the right hand rule is important. It's not necessary you can get away with the left hand rule also, but you will be alone in there, and most of the things are written in terms of right hand rules. So most of the time things are convenient when you think of the contour as counterclockwise, but surely not necessary, and we will talk about those things. So this is what we are saying. There is an integral I which depends on A, so A can change, so you can redo this integral so for different A's, and we are going around this complex that on a contour on this plane, and f of z is analytic and z minus a is in the denominator. Clearly at z equal to a, it blows up, so it is not analytic at z equal to a, right? So if I were to draw a contour here, so let's call this contour C, and let me say that is a contour C1, right? So what can I say about C1? Is z f of z equal to? How much is that equal to? 0, right? Because f of z is analytic. What about z minus a? First one was true because of Cauchy's theorem. What about f of z over z minus a in the contour C1? Yeah, it is 0. Good, very good. And why is that? Yeah, it does. Z minus a is analytic everywhere except z equal to a. Z minus a is 1 over z. It's a simple function, except at z equal to a where it blows up. So that is its problem. So you avoid that z minus a. So here it is completely analytic. So it is an analytic function multiplied by another analytic function. So you get back your analytic function because this is equal to 0 because 1 over z minus a is analytic in C1, inside C1. But that's not useful. I was just trying to point out what I mean by this, how the contour depends on one. This is not relevant for us. We are really interested in this. So for this purpose, so what I do, we do a trick again. So let's do this. So we have A. That's my point A. It is analytic everywhere except at point A. So what I do is I do the same contour C here. This is my contour C, but I change this. I introduce a new contour now. Somewhere from contour C, I deviate. So I'm coming here, go in this direction, then go around this point, and then come back. So this is C, and this whole thing is C1. Let's call it C2, and then I call it C3. C1 and C3 are going in opposite directions, so they cancel out. So it is C and C2 that is remaining. So C1 and C3 cancel out. So what I have done here is that I have isolated that point somehow. Right? So I can say that I of A, which is on the contour C, or let me say this again. So if I'm now doing this integral now, dz, and this is the trick I should mention, the kind of tricks you do in contour integrals is all about choosing the contour. So notice what I'm doing. I'm interested in f of z minus za, but I'm not going to do those contour. I'm going to change the integral completely. I say I do the integral from C to plus C1 plus C2 plus C3. And what is that equal to? It is 0. Very good, because now the pole or the point that was having this problem of non-analyticity is outside my contour. Inside this contour, it is, so this is what is in my contour now. The region covered by my contour is everywhere except that point. So this is equal to 0. Because the contour C plus C1 plus C2 plus C3 goes inside the contour. All points are fine, let's say. By fine, I mean it is analytic everywhere, and my Cauchy theorem works. C1 and C3, we argue that it is the same, so I can say, notice the argument, C dz f of z over z minus a plus, let's call it C1 plus C3 dz f of z q that's equal to 0. Notice I'm really not doing any integral. I'm just playing around with the geometry of the contour. This one, I know what it is. This is my I. This is what I'm interested in. That's my contour I that I'm interested in. This is 0, C1, I go one direction, C3, I come back in the opposite direction. This is 0. In opposite direction. Which means that if I'm interested in integrating I of A, I just have to do the integral in some other contour, which contributes to that. It is like saying that if I want to calculate the potential energy change when I'm going from here to the ground floor in the parking lot, I don't do that. I know that when I'm going horizontal, I don't do any work by gravitational energy, so I just go vertically down. So I don't take the path of the whole staircase and go down because that's too complicated. I take a simple path which is going straight down. Same thing here. I can do this whole contour, but I want a convenient contour. And I know that that is equal to the negative of that. So I will do the contour on a circle, going as close. I can hug it to this pole. You will call this a pole now. And I can make it as small as I want. It can be infinitely tiny and perfectly fine. I'm good with it. So that's the trick I'm going to use.
See whether the function is 1 over 0 goes to infinity. Not
It will be not analytic. Yeah, anytime it goes to infinity, it is because then you cannot verify the Cauchy-Riemann condition, right? That's one way of looking at it, but that is a very simple way of looking at it. But what you can say is that whenever you have 1 over 0 coming in, that is not analytic at that particular point. It can also be 1 over z squared, 1 over z cubed. So this will be called a first order pole. 1 over z square will be called a second order pole. Most of the time we will be working with first order pole, but it's very easy with second derivatives. It's almost an immediate generalization. But with the limited features or limited time we have, we might first put our pole. Or let me not say like, yeah, I may not ask you too many questions on that, but I have taught you the expectation of generalizing to that. So I answered your question, right? Yeah, it is called a pole. So it's pole, so you give it a meaning to it. It's again, compare it with electrostatics. If you have divergence of an electric field, on the right side there is a source, right? If there is a point source, you get an electric field, right? And point source is the charge. It can also be the first derivative of the source. That's a dipole, point dipole. That also creates an electric field. Second derivative of a point charge, which is a quadrupole, that also creates an electric field. Same idea here. There is a first order pole, second order pole, third order pole, they all contribute. And what I'm going to show here now is that this pole, it will be like a delta function. This is going to be f of a. Think of this like a delta function. Like delta function evaluates a function at the point a. But you don't say it's a delta function in complex analysis ever. Like it is a pole, and it is so. But what it is doing is that it will give you f of a. So that's what I'm going to show in a moment. That if you have a pole, it will give you f of a, and that's called a residue. So that whole analysis will be called a residue. If you have done, how many of you have done complex analysis in some form, like at least a language? Have you heard? I haven't introduced it. So when I say residue, does it? So you have residue. It can be a stereotype and say that you're from Pakistan. How did you done? Sorry, stereotyping. Sorry. So, Nahida, residue? No. That's okay. Yeah, you guys. Never know. Have you done a complex analysis? A little bit here, but no residue. Yeah. Okay, that's fine. Sorry. It's yeah. Okay. So I not introduced residue, but I'll do it whenever necessary. I will do it. We are almost there. Okay. So we want to evaluate this integral, but we won't really do the integral, but we will see how we are going to go over. So I use this. This is Cauchy's theorem now. Cauchy's theorem tells me that I of A. I'm not interested in this contour because that's a complicated contour. Instead, I pick a simpler contour, which is a circle really hugging the whole. Let's me define this now, right? So this will be a pole. Whenever I have a function 1 over z minus a at z equal to a, it goes to infinity. That will be called a pole. It's just a nomenclature, but for our purposes, it just goes to infinity. That is an important thing, that if it goes to infinity, you don't know how to deal with it. So that's the basic. Right? So this is equal to minus because I take it to the right hand side. But now I do integral on C2 dz f of z over z minus a. And C2 is a circle. C2 is a circle. So this is A, and C2 is a circle. So that's your C2. Let me go in the counterclockwise direction. And let me give it a radius for that circle. This is, let's say, epsilon. Epsilon, meaning that it can take a very small value. Usually, you associate infinite small values to them. So that's my integral. This integral C2 is along a circle which is very close to the A. To evaluate this, now I'm going to do that integral on the circle. What I do is, this is a complex number. So z minus a, I can make a substitution. Remember your polar coordinates, that's epsilon e raised to I theta. This is that complex number on the circle, right? That will be epsilon e raised to I theta plus the a, the center point, right? We have to add to that. And when I'm integrating, now it is clear that I'm keeping the epsilon constant and doing the integration on theta. And I go around C2, I'm going around theta. So that's what I want. But dz now is equal to A's constant, and this is I times epsilon e raised to I theta, e theta. That's the same as I z theta. I don't want to write it. I can leave it like this. So I suppose it's unnecessary to identify it. So I of A then is equal minus C2. Now I'm going on this integral theta, so it is 0 to 2 pi. It's actually going in a complete circle, so it is 0 to 2 pi. We will do more integrals of this kind. The contour need not be the full circle. Sometimes it is half the circle, then you have to go 0 to pi or pi to 0. It is sensitive to where the limits are. dz is I, epsilon e raised to I theta, theta. F of z, it is f of z is a plus epsilon e raised to I theta divided by z minus a equals epsilon e raised to I theta. If you remember when you're doing the Gauss's law for a point chart, you will do the integral on a surface of a sphere, and the radius cancels out, like radius square cancels out 1 over r square. That cancellation plays an important role to evaluate or use Gauss's theorem. That is this cancellation here. Notice this cancellation. This is divergent, remember. Z minus a at z equal to a, it is going to infinity. But while you're doing this integral, it cancels out. It's no more infinity. This is the x over x, sine x over x limit of sine x over x is 1, right? This is the crucial step that is actually saving you. You would say that, oh, I cannot do this integral, there is an infinity there. I'm not even going to attempt that. But no, there is this nice cancellation that allows you to do that integral. That cancellation is everything. That is the concept or the geometry behind this. You have to look for this cancellation, and whenever that cancellation is possible, you can do such an integral. From this point on, it's just a matter of doing it. This is minus I 0 to 2 pi d theta, and the function is a plus a very small quantity. I'm really taking the limit, so I should take the limit, like limit epsilon tends to 0. So when I drew that contour, I could have picked any contour, so I specify the contour that this is not just any circle. I can make it as close to the pole as I want, and if this is here like this, then I can make this as small as I want. As far as a is not 0, or f of 0 is well defined, I can make this as small as I want. I can neglect this, and this is 0 to 2 pi theta. I can't neglect this because all the divergences were in the denominator that cancelled out. This function was analytic. Right? The whole idea that it is analytic means that if I make a small change, it is not going to go to infinity. Right? A function is analytic means that it is well behaved everywhere. It's not going to go to infinity anywhere nearby. So that's important. So that's f of a. Taking in the limit epsilon tends to 0, since f of z is analytic, it is well defined concept there. In the first time you're doing it, it's not easy to accept. Okay. If that's the case, it comes out. What happened to my son? So this is equal to f of a minus I f of a, and that's 0 to pi d theta. Just write it down more steps. So that's 2 pi I. That's equal to minus 2 pi I times f of a. What happened to the minus? Where did the minus? We choose the other one. Yeah, so maybe let me try. So this is C, right? I come here. Oh, yeah. So this is P. So then I go this way. And then I have to come this way. Correct? That's what we're trying to say. If I go this way, then I have to come the opposite way. Yeah. So contour C, since it was counterclockwise, I did not have a choice. This had to be in the opposite direction. Otherwise, I'll be crossing the contour. Like crossing the contour is not okay. At least we'll come to that. Those are other features that will come in. We'll talk about branch point and other things. Yeah, good. Thank you. So that helps. So this one is then, what did I do? So now C2, I did not draw an arrow there. So I'm safe here. I do that. And the only thing I have to change here is now it's 2 pi to 0, right? So it is 2 pi to 0, right? So I change that. My bad. I should not have confused. And here I will stay on the side. Okay. And then sorry about that. So otherwise it would have been a clean up. So the statement is if I summarize this, let's summarize this here. Summarize this here, that remove the I so that I have this. Yeah. if I write this as q pi I, contour, a closed contour where f of z is analytic, 1 over z is not analytic by construction because it goes to infinity at z equal to a. Now this is equal to f of a if a is inside contour C. So that means that there is another possibility that, and that is if A is outside contour C, right? And that we already did. We kind of argued what would be the case for C1, right? And that was immediate, like Abdullah immediately said that that would be equal to 0. So that's equal to 0. And that is what I was saying. This seems like a delta function, right? This is, if you think of this as a delta, 1 over z minus a as a delta function, that has those features in there. So geometry wise, it's very similar. But remember, this is a two-dimensional plane. Like the entirely different space we are talking about, complex plane, complex multiplication, that is complex division. Vector space doesn't have division at all. So it's entirely different things, but there is a lot of symmetry, or there is a lot of analogy in the geometry, that there we talk about delta function, here we talk about pole. And this is called the residue. So, and in fact, this is such a powerful thing that if I were to now ask you to do an integral, let's say example again, so the last 2 minutes. So if this is a complex integral, let's say exponential of I z times sine hyperbolic of z, and divided by, let's say, v divided by z, right? And if I say this is a contour that is, specify the contour, let's say this is radius 1. That's a complex plane with unit radius. Remember, it doesn't really care for the contour. What is that integral equal to? 2 pi i's, right? 2 pi I. Notice how Arjun is doing, and then, yeah, go ahead. So you evaluate this, get rid of the z, and e raised to I z sine hyperbolic z. Evaluate this at z equal to 0. That's it. You finished an integral. I could have written any analytic piece there, and you know the integral. The idea is to isolate this pole. If you have more poles, use use partial fractions to make 2 integrals out of it. Right? So this is equal to 2 pi I. So this is the residue now, right? Exponential of z is 1, and sine hyperbolic of 0 is 0, right? Is 0. Let's answer is 0. If there are more than one pole, use partial fractions. 1 over z minus a and z minus b. If you have 2 poles, then you can always think of partial fractions. Find a. You can write this as, first find a and b, and then there are 2 integrals. So as a whole class of integrals, you can immediately do using residue theorem. So, but uses a very simple idea that around the pole, or around the pole, if you go, it is the value of the function itself. I'll stop here, and we'll come back and do more integrals, more interesting integrals. If you, we'll talk about causality. Yeah, causality involves a step function, right? Like, and we will see that we will have to do complex integrals there. So it's kind of a nice thing. I'll stop here. Okay.
Thank you, Dr. Sajesh.
Bye, Niranjan. Yeah. So Nathan, you did take a complex numbers course, you think? Or have you done a course on complex analysis?
I didn't take a course on it, but we talked about.
Oh, just here and there, okay, yeah. So you did a course on complex analysis?
No, I didn't. It's mathematics courses in undergrad.
But not complex analysis, no.
They were like mathematics and, but it included the portion. Okay,
Okay,
yes.
thank you, Nathan. Oh, Aryan, I have a question for you. Did you reply to me or?
I'm listening.
That's okay, so what, so this is the following, I wanted to write that, I think I was, no, don't worry. No, I think so yeah. If something happens at the end. You cannot blame me, but hopefully not. I think so. After the first week, I get a feel that nothing wrong is gonna happen. I manage the procedure. So, because I thought